Hello. Today we're going to discuss three problems with game theory. Now, normally when people talk about the flaws in game theory, they get to human rationality and they point out correctly that people aren't rational, but game theorists usually assume people are rational, therefore we have all these problems. And those are certainly a legitimate class of problems. But with this video, I'm going to look at three problems that arise even when you assume that it's common knowledge that all of the players of the games are super and completely rational. The first problem we're going to discuss arises with mixed strategy Nash equilibria. So consider the game in front of us. There's no pure strategy Nash equilibria, but there is a mixed strategy one in which A and B are each played with probability 0.5, and X and Y are each played with probability 0.5. Now remember, a Nash equilibrium is a no regrets outcome. So if all of the players are in a Nash equilibrium, that means what each player is doing is a best response to what all the other players are doing. Now in this game, playing A half the time and B half the time is a best response to player 2 playing X half the time and Y half the time. But that's only because if X is played half the time and Y is played half the time, player 1 is indifferent among everything, including all possible mixed strategies. So think about player 1's optimal choice if player 1 believes that 2 is going to play X half the time and Y half the time. Well, given that X will be played half the time and Y will be played half the time, if you play A, half the time you get the 1, half the time you get the 0. And if you play B, half the time you get the 0 and half the time you get the 1. And if you play some combination of A or B, still half the time you'll get 1 and half the time you'll get 0. So you are completely indifferent among everything if you're player 1, if you think player 2 is going to randomize at the 50%, 50%, with the 50%, 50% strategy. But this means that you're completely indifferent among everything, including a Nash equilibrium. So why would you ever want to play your Nash equilibrium? It's true you wouldn't object to playing it, but there's an infinite number of things you could play. So it does seem kind of weak that game theory would say, oh, this Nash equilibrium is special. It's true in this game there's only one no regret equilibrium, but the players have no reason to reach this. And in general, this is a problem with the mixed strategy Nash equilibrium, that the players don't regret being in it, but you only get a mixed strategy Nash equilibrium if all the players are indifferent among all their pure strategies that are part of the mixed strategy Nash equilibrium, or indifferent among any probability mixing of these pure strategies. So there's no reason the players would ever want to stick with the Nash equilibrium. And this, again, I think this is a big problem in game theory, because when you have the game in front of us, none of the pure strategies make sense. The mixed strategy Nash equilibria, we can't rule it out, but we really don't have a strong reason to rule it in either. The next problem in game theory I want to discuss arises in the game in front of you. Let me read this out loud. Two players each simultaneously write down a number between 0 and 1,000 inclusively. Inclusively just means you could write down 0 or 1,000. The player who writes the lowest number gets that much in dollars. So that just means if player 1 writes down 300 and player 2 writes down 400, player 1 ends up getting $300 and player 2 gets nothing. If the players write down the same number, they each get half of what they wrote down. So this just means if player 1 writes down 50 and player 2 writes down 50, they each get 25. And we're going to assume money is continuous. So you could write down not just $38, but you could write down 38.3016 or 0.001 or 98.283. You can pick any real number between 0 and 1,000 inclusively. You get that amount in dollars, and we forget the fact that the smallest amount in dollar units is a penny, or we just pretend, if you get 1/10 of a penny, that's getting a 1 in 10 chance of having a penny. So why don't you pause this video and try to come up with what the Nash equilibrium is. What would rational people do in this game? Okay, I've assumed you've thought about the answer. And there's a surprising result, and that result is that both people will write down 0. Now, to see why this is the only Nash equilibrium, imagine the two people write down any other number. Let's say they both write down 3. Well, if I think you're going to write down 3, I don't want to write 3. I want to slightly undercut that. I want to write 3 minus a little. If you write down 1 cent, my best response to that 1 cent is to write a little bit less than 1 cent. So for there to be a Nash equilibrium, both players would have to have beliefs about what the other person is doing, and those beliefs would have to be correct. And then each player's, what they write down has to be an optimal response to their belief. And if the only way this can work is if everyone writes down 0, right? If I write down 0 and you write down 0, well, given that I've written 0, you can't do better than picking 0. And given that you've written 0, I can't do better than picking 0. So we're both playing optimally given what the other person did. But anything else, that doesn't work. Because if we pick different amounts, if I pick 4 and you pick 8, you'll regret picking 8. You would have wished to pick a little bit less than me. And if we pick the same amounts, we'll both regret not having slightly undercut the other person. Because, even if we both write down 1 cent, I would rather write down 0.99999 of a cent and, get all of that than share 1 cent. Of course, given that, 0, 0 is the only Nash equilibrium, the massive problem with writing 0 is that it's a weakly dominated, or the terminology I use is weakly stupid strategy. I mean, you think about it, 0 is the worst possible thing you can write down. If you write down 0, you are guaranteed to get 0. If you write anything else, you've got a chance of getting above 0. So it would seem that the stupidest thing you could possibly do is write 0. There's an infinite number of choices, all of the real numbers between 0 and 1,000 inclusively. And 0 would seem to be the worst. But that's the only Nash equilibrium. That should cause us some worry. And this comes up a lot in game theory, where the only reasonable equilibrium, or the Nash equilibrium, is the weakly stupid strategy, the weakly dominated strategy. And this is a big problem with game theory. The final problem with game theory I wish to discuss with you today is involved in the game in front of you. So please pause this video and give some thought to what's the reasonable outcome in this game. Okay. Well, the first thing you should use is that for player 1, B is a stupid strategy, right? If player 1 picks C, you get 5. You're guaranteed 5 if you're player 1 and you pick C. If you pick B, you're guaranteed 4. So, well, if you're player 1, you shouldn't pick B. If you pick A and you're player 1, well, you might get 6, you might get 0. So for player 1, we don't know which is better, A or C, until we've at least looked at what player 2 is going to do. But player 1 should say to himself, B is definitely out. Now let's look at the game from the point of view of player 2. Player 2 would say, well, okay, maybe C is going to be played and I'll never get to move, but if I do get to move, then I know C hasn't been played and I know either A or B, and I can't directly observe that. Well, if I somehow knew that A was played, if I knew when I got to move and I'm player 2, I'm on the left, I would want Y. But if I knew when I got to move that B had been played and that I was on the right, I'd want X. So player 2 should say to himself, okay, I can't figure out what I'm going to do until I figure out what player 1 would do. But then when player 2 looks at what player 1's going to do, player 2 should say to himself, oh, but B is a stupid strategy. Player 1 is never going to pick B. Maybe A, I'm not sure, but, maybe C, but certainly not B. So if player 1 doesn't pick C and I'm told I get to move, I should assume that player 1 picked A, and me as player 2, well, if I know A has been picked, I want Y. So player 2 should say to herself, maybe C will get played, in which point I don't get to move, so my beliefs don't matter. But if I do move, I'll have the belief that A was played, and then I'll play Y. And that leads to the following solution for this game. So if player 2 will pick Y if player 2 gets to move, then player 1, taking that into account, will just pick C. So the way the game ends is player 1 picks C, and then player 2 never gets to move. And I think this is the best solution for this game, But there's still a massive, massive problem with this solution. And the problem is, what if player 1 doesn't go along? What if player 1 ends up picking A or B? What should player 2 believe? Now, player 2 can't just believe that A has been picked, because the logic of, B is stupid, therefore 1 will never pick B, therefore 1 will pick A, that leads to thinking that if player 2 gets to move, player 2 will pick Y, but that leads to player 1 immediately picking C. So this means that player 1 would never pick A or B. So what should player 2 believe if he gets to move? You see, player 2 has this great story that works, but only so long as player 2 never gets to move. And if player 2 does get to move, I don't know what she'll believe. The general problem here is game theory has a problem figuring out what a player would do if she got to move in a situation in which she expects to never move. Now in this game, 1 is picking C because of what 1 thinks player 2 would player 2 would do if player 2 got to move, right? Because player 1 would rather get the 6. So if player 1 thought that player 2 would respond with A with X, player 1 would pick A. So what player 2 would do if player 2 got to move, that is really important to player 1 figuring out what player 1 should do. But how can player 1 figure out what player 2 should do if player 2 gets to move when player 2 has to think she should never move? Because if player 2 actually does get to move, she'll say something like, wait a minute, maybe player 1 is crazy, or my whole thought process completely breaks down. So again, the big problem in game theory is if say I can't figure out what I'm going to do till I figure out what you're going to do, but I think that you'll never get to move, and I think that you think you'll never get to move. But if you do get to move, then something really weird has happened. So how can I come to a belief about what I think you'll do if you get to move, when I think if you do get to move, you'll be really, really confused because you expect to never move? Thank you for listening to me today.